All right. Hello, everyone. Welcome to today's installment of the Corundum developer meeting. I got a bunch of stuff to talk about today, so I'll I'll try to move as quickly as possible here. Okay. I got announcements and then status updates, so let's get into it. All right. So the announcements, the next developer meeting will be on July 2nd. And then the next Switch developer meeting will be next week on June 11th, assuming Carlos has something to talk about. So we'll see about that. Keep tabs on the Zulip for information on that. Um, yeah, moving on to the status. I got. I'll just go over briefly what I've been talking about previously with deprecations of the rewrite progress. I've been doing a lot of work on the MacFi GT wrapper stuff, and the big news on that is adding support for the low latency synchronous gearbox mode. So that is not totally complete, but it is functional for sending and receiving packets. What needs work is some of the time stamping related stuff. And then I've been doing some longer term planning both for Corundum and for the networking stack. I had a UDP stack in the old Verilog Ethernet repository that was kind of a little bit rudimentary. So the idea is to build a new one of those. Hopefully, that's going to be much more usable. And then also, a new version of Corundum as well, built on System Verilog. So I'll talk about that a little bit. I've also had some people ask about virtual device support, and my answer has always been, well, if I don't have hardware, it's not going to happen. I recently got access to a bunch of VCK 5000 boards, so there's now the possibility of adding support for Versal. Unfortunately, that's a slightly different part than what's on the V80, so hopefully I'll be able to get a V80 at some point, and then we can get Corundum running on the V80, but that's a longer term thing probably. Um, the VSK 5000 out of the box is not technically supported by Vivado. Xilinx keeps that under wraps, so I had to do a little bit of work to figure out how to make it work, but I did. So I'll talk about that a little bit, and then I also took a somewhat deep dive on the Versal architecture documentation to figure out, okay, well, if you wanted to run Corundum on Versal, what would that look like? So I got some notes on that about what I learned, and spoiler alert, I'm not very impressed with the Versal devices. So more on that in a few slides here. All right, so just going over the deprecations again. Basically, all of the Verilog code that I have on GitHub is going to be deprecated eventually. I've added deprecation notices to a bunch of things. Everything else will eventually get them as well. All of the stuff is going to be superseded by Taxi. So the idea is that the functionality is going to be nominally the same. It's still going to be available as open source if you want to use it for research or whatever. If you want to use it for commercial applications, happy to support that as well. Just um, pay a license fee, and we're good to go. And also, there's some news on this front. I got permission from MLE to use their core license agreement. So I still got some more, business side of things to get set up on my end, but at least I don't need to pay a lawyer a bunch of money to write up a license agreement because they have one that's MLE has one that's kind of trial by fire. It had modifications from several major companies, who have licensed the cores and, needed modifications and extensions to the license agreement. So it should be a pretty darn good starting point, I think. But yeah, feel free to reach out on Zulip or via email or whatever if this is interesting. Um, yeah, so moving on, System Verilog rewrite. Talked about this before. The plan is to rewrite basically everything in System Verilog um, such that we can support kind of this dual open source model and also commercial licensing for just being able to support the project generally and the maintenance going forward in the long term. So I have the new taxi transport library I'm putting together, and I'm in the process of porting everything over to that and implementing new functionality in the taxi library um, that's going to be useful. So I have example designs for several different boards at the moment, and some basic Ethernet functionality working. There's still a number of things that need to be ported over. I'm just going to blow through the tooling status stuff. I should probably remove a couple of these slides because nothing has really changed. The system Verilog interfaces certainly reduce the amount of code you have to write and reduce the possibility for errors. So that's great. The porting progress, actually, I haven't really ported too much more. I've started to work on some of the PCI Express stuff. Um, did I create another sync primitive? I I'm not sure if I've created any more sync primitives at this point. There's a couple that I've been working on off and on. I was going to do a pulse sync and then a gray coded sync for the FIFO modules, but I haven't had time to work on that in a while. I have started to take a look at the PCI Express stuff, um, because that's going to be the plan to port all that over, get that running on the ultra scale devices at least initially, and then continue to expand on that. Um, I think some of the PCI Express stuff I'm not planning on doing a direct port, because I am considering tinkering a bit with how the components work internally. But there is something to be said for just doing a direct port to have something and then going back and making modifications later. So that kind of remains to be seen once I get a few things cleared out, to really sink my teeth into the PCI Express stuff and get that squared away. Long term, um, the idea is to build a new UDP stack instead of porting over the old one, and more details on that in a couple of slides here. All right. So I guess the example designs I have. Oh, that's one thing I forgot to mention earlier is I did a significant reorganization of the taxi repository to basically keep all of the subcomponents together. And one of the things that I did is I actually moved all the current reference designs under the Ethernet folder. So those are going to be mainly Ethernet plus some supporting components. So those example designs are basically just going to bring up Ethernet plus, XFCP and monitoring type stuff. Um, I'm not sure at this point how I'm going to handle the DRAM and the AXI stuff, um, but I'll probably have example designs under some of the other subsystem folders as well. We'll see about that. But yeah, I have example designs for a bunch of different boards. I think I've added a couple more. I can't remember offhand which ones. I know I added a bitware one recently, maybe another one as well. Um, yeah, but there are a bunch of example designs there to take a look at. I don't have anything for Intel devices yet because I have to figure out how to handle the transceivers and stuff properly. Like with the Xilinx devices, the TCL support in Vivado is a lot better than the TCL support in Quartus. So that's squared away and pretty clean for Vivado. For Quartus, I need to do some back to the drawing board and make sure I have a flexible and extensible way of handling the Intel devices. Um, all right. So I've also been working on, new MacPhi and GT wrapper. This is kind of based on what I put together for Corundum, but reworked and reorganized a bit. So this wrapper uses the combined Mac and Phi module instead of just the Phi, and then you have the Mac in the core logic. I also have it set up such that you can actually put the whole wrapper in the core logic, which means you can test with all of the management HDL as well. Basically, it turns off the GT instance, but everything else is in there, so everything else can be tested. And then the simulation model attaches to where the GT would attach. Um, and this is using a much more modular design. I have modules for like the reset, for reset synchronizers, and then also for all of the reset state machines for the QPLLs and for the channels. I got that all sorted out. Um, I've got the statistics integrated, and I also have the very recently integrated the synchronous gearbox support buffer bypass and whatnot, which required stringing a few additional signals through some of the data path. So more detail on that in a couple slides here. But now that I have the gearbox support, some of that's actually going to make it a lot easier to add support for things like USXGMII, where you have to do symbol replication. And from the standpoint of the Mac and Phi levels, I think that's going to sort of act like the PCS or act like a gearbox, but we'll see. We have at least some of the infrastructure in place for that. All right, so the 10 gig, 25 gig low latency mode that I put together, I guess I just added this last week, right? So at a high level, it's basically just one added parameter to the wrapper. And this wrapper, it puts it in low latency mode. So I added a new GT wrapper that sits kind of a few levels down inside that's just around the GTs and a little bit of supporting logic. The TCL scripts have been updated to generate both GT variants, so you don't need to include different TCL scripts or anything. You just need to change that one parameter to put it in low latency mode. And I've updated all the Mac and Phi and common logic to support the signals necessary for the gearboxes. The reason I didn't just switch everything over to this and I have this parameter is because there's a bit of a timing and area trade-off. So the clocks do run a little bit faster in the low latency mode, and you need some additional logic for the sync and stall signals that synchronize the transceiver gearbox with the data path and clock enables and whatnot. That increases the footprint a little bit. So if you're on a part where you're really timing constrained and area constrained, you probably want to run it in the normal latency mode instead of the low latency mode. So with this parameter, it makes it really easy to decide which way you want to use things. Um, okay, that slide didn't work properly. So what's the story with the gearbox? Well, the problem is that the 64-bit, 66-bit code operates on 66-bit blocks, but serializers are generally powers of 2 plus maybe a factor of 5 in there somewhere for AP10B, but 66 is 2 times 3 times 11. So nobody's going to build a 66-bit serializer. So what we have to do instead is we use a 32 or 64-bit serializer, and then we repack the data into 66 bits. But the problem is that if you bring in 64 bits and you out per cycle and you output 66 bits, you can't output for every cycle because at some point you're not going to have enough bits to output. So you need to insert stall cycles somehow. So with a synchronous gearbox, everything runs in the same clock domain, but the data path has to be stalled in synchronization with the gearbox such that everything works properly. And also the effective latency variant varies cycle by cycle because the gearbox is going to have different amounts of data stored in it, and that is effectively the latency, even though it's always like one clock cycle through because the bit positions are different. That's effectively the different latency. Um, the async gearbox is basically exactly the same as the sync gearbox, except you add an asynchronous FIFO, and then you use a clock that has a different division factor to absorb these stalls. So this is why, for the 10 gig async gearbox configuration, it'll use 156 internally because that works perfectly without, or the ratios work out perfectly to where all those stalls will be absorbed by the FIFO. The interesting thing that I noticed is that the latency is with the async gearbox is actually constant on a cycle by cycle basis because effectively it's just sloshing around between is latency in the gearbox or is in the FIFO as the clock phase changes throughout the gearbox cycle. It's going to move from one to the other. But the problem is that latency changes every time you reset it. So that becomes a significant problem if you want to have consistent latency for timing applications or whatever, because there's no easy way to measure that. So with the sync gearbox, you get the advantage of it's all in the same clock domain, so you don't need the latency of a FIFO, and you can actually figure out exactly what the latency is because you could look at the gearbox state and make the appropriate adjustments. So this is what. A second, I guess. How do these slides get mixed up? All right, so I had to add a couple signals for this to work. On the RX, it's actually pretty easy because all we need to do is add a valid signal, and then the data path just needs to be pipelined appropriately to handle that. But on the TX, the situation is a little bit more complicated because we have to generate the correct stall sequence at the end of the transmit pipeline. So you have to feed something into the transmit pipeline at some point, which can then propagate down correctly and then produce the sequence that we want at the output. And this needs to be done in a way that you can connect it to basically any transceiver and have it operate correctly, right? I don't want to be baking in transceiver specific knowledge into like the PHY module because that would make it harder to run on different transceivers. And even with the Xilinx transceivers, if you change the internal width, right, that changes the gearbox sequence. So like with the GTH transceivers, they use 32 bits internally, 64 bits externally, versus GTY at 25G, you do 64, 64. The gearbox sequence is different. So, how do you handle that? So the GTs also require this TX sequence value to be provided on the transmit side. So my original idea is to generate that TX sequence and then make a loop, right? So that'll be generated in some logic near the transceiver. Then that gets sent into the data path somewhere, like the phi, perhaps phi or MAC, and then it propagates down back to the transceiver. And if the delay of that is the same as the delay of the data, then everything works. But what I realized is that, well, instead of adding all those additional bits for the TX sequence value, which I think is 6 or 7 bits wide, what we can do is just have a single bit for synchronization and then have another counter that generates the TX sequence. So that ends up producing a really simple interface where we have a stall signal and a sequence start signal that gets sent into the data path. And then the data path that stalls when the stall signal is high. And then it has to propagate the start signal alongside the data all the way to the end. And the idea is that you'll get the same relative timing between the stall signal and start signal where you actually feed into the transceiver at the end. So when you implement it, it looks like this, where we have these are the request signals, right? We have the stall signal, we have a 2-cycle stall, and then a 1-cycle pulse on the start. And then at the output, we have the gearbox, or the transmit data valid into the gearbox, goes low for 2 cycles, and then immediately after we have the gearbox start pulse here. And you can see the TX sequence value generated up here. So 0, 1, 2, 3, all the way up to 31, 32. And on cycle 32, that corresponds to when the data coming out is, or the data fed into the gearbox is not valid. So this seems to be, this is doing what it's supposed to do, right? And this is, I think, running back-to-back minimum length frames with the network tester. So yeah, so this works with the network tester, and the receive path is basically doing something similar, but like I said, it's a little bit simpler because you don't need the extra counters and whatnot. So the status on that, the main data path modifications are done at this point. I've tested it on several different FPGA boards, the BC118, BC108, KC105, and CC106. Basically just all the combinations of UltraScale, UltraScale Plus, and GTH, GTY. I have a strategy to track the state of the RX gearbox. I haven't implemented it yet in the hardware, but I have an idea of how to do that. And then let's see, for the timestamp correction, I still need to implement that and then potentially see if there's some optimizations that can be made to improve the timing performance or, shrink things down a little bit. Longer term to do, maybe we can do an ultra low latency version. I don't know. It's not a very high priority because raw latency, at least for me, has not been a particularly high priority. It's more about getting the consistent latency for the timing. I've also looked at 7 series support. I figure, well, I know the 7 series requires the synchronous gearbox because they don't have the async gearbox, but the wrinkle is that due to differences in the FPGA clocking primitives and clocking structure, it's unclear what the best approach is. So I'm gonna have to table that for the time being, and potentially circle back to that down the road at some point. We'll see. I mean, if somebody's asking about 7 series support, maybe, but until then, yeah, it looks like it could be a bit complicated to make that work. I say 16 clocks per quad if you use all 4 channels, but if you just have 1 or 2 ports, I guess it's probably not as big of a deal. Yeah, so that's the synchronous gearbox. It's looking pretty good at this point. All right, so moving on to Corundum. So what I'm thinking about doing with Corundum is not doing a direct port of the existing design as it is, but instead to build a couple of new designs that do something very similar. So I've had a couple people ask about, hey, could we have like a smaller, kind of light version of Corundum? Because with the control logic, that doesn't scale with the data path, right? With Corundum, you can go in, you can say, yeah, well, I'm only using gigabit max, so I just need an 8-bit data path. You save some logic resources in doing that, but then you still have, the descriptor processing stuff that is 128 or 256 bits wide or whatever. That doesn't really scale, and the schedulers and everything else. So what I'm thinking about doing is building a couple of different variations. So the first one, Corundum Micro, is intended for SoCs, and it'd be a really small size optimized design that's just supposed to support a handful of ports at 1 gig. And then Corundum Lite is maybe somewhat similar to, the current Corundum design where you have a handful of ports at 10 gig or 25 gig, or maybe one port at 100 gig, kind of 100 gigabits per second or so maximum, aggregate bandwidth across all the ports. And then, or maybe even less than that. I'm not 100% sure. And then Corundum NG would be the maximum performance design, right? So this is where we'd be looking at, 400 gig potentially performance. And the idea is that all of these would use the same driver, and they'd all support timestamping, checksum, and segmentation offloading. And then hopefully we'd also be able to get DPDK to work with all of these. So just to go into a little bit more detail, Corundum Micro, sized optimized design. At this kind of rate, we're talking about, lots of clock cycles per packet, right? So you can potentially even, I'm not going to say do this in software, but you can take more of a software-like approach, maybe a microcoded design, something like that, which can really reduce the size of the setup and trade off, you know, reducing the area for, longer pipeline, or not so much longer pipelines, but more cycles in performing various operations, and also potentially sharing more of the internal logic as well to help reduce the size. And this is really intended kind of for SoC use. So primarily it'll have an AXI interface, but potentially this could also support PCIe. And the plan is to implement a lot of the basic NIC offloads, so segmentation and checksum offloading, scatter gather DMA, timestamping primarily. I don't know about really much beyond that at this point. Stuff that would give you some decent amount of advantage on an SoC where you don't have a particularly powerful CPU, right? What are you doing, kitty? Can you quiet down? Ah, that guy really needs a lot of attention. Um, anyway, so the idea with Corundum Micro is that the core is going to be pretty self-contained. Um, it's not going to be like a top-level design like the current version of Corundum. Just drop it into your setup, connect it to a couple of ports, and you're good to go. One thing I also realized is that this could be a pretty good mechanism for prototyping the new descriptor formats and developing the driver, because it's a much simpler design. We can hopefully get it implemented more easily, more quickly, versus trying to not only develop the new format but also deal with it with a high level of performance. That adds a lot of additional complexity. So I think it could actually work out to being a very good stepping stone from a prototyping perspective. All right, so moving on to Corundum Lite, the idea is that this one's going to support a handful of ports at 10 gig, 25 gig, maybe one port at 100 gig. While Corundum Micro only supports one queue per port, Corundum Lite would support multiple TX and RX queues, SRIOV, that sort of thing. This is also the size where it could make a lot of sense to use on like a Zinc device. So to support both PCIe and AXI for the host interface would make a lot of sense. So very similar to the current version of Corundum. And it might also support dual heading. I'll have to see about all of the details behind that, but that could be a useful feature for MPSoC devices. Maybe it'll have an application section. Not 100% sure about that. And it may also be available as a self-contained core instead of a top-level thing. Which definitely, if you're trying to use it as a on a Zinc device, it makes sense to have a self-contained core you can just drop down and use. Right, so that's Corundum Lite. And then Corundum NG, this one is designed to be the highest level performance. So the plan is to target the Intel Agilex I R tile, 500 megahertz, 1024 bits for PCI Express. That's the Gen 5 by 16. I don't know if we're going to be able to get stuff to close timing at that kind of clock rate, but we'll see. And the idea is this will also support other devices. So it's not going to be limited to that, but the idea is to start with that because that's kind of the highest performance level core. Like the Versal devices don't support Gen 5 by 16. They only go up to Gen 5 by 8. So that's a slightly different level. Um, I'm going to look into supporting multi-headed PCIe because there's seems like there's a lot of cards, and particularly the Versal ones that support bifurcated, dual Gen 4 or Gen 5 by 8 instead of, a single by 16. Um, so that could be a useful feature to have. And I'm also going to look into PCIe AXI dual heading. So if you had like a Versal device, then um, you can, the Versal can also interface with the Corundum logic directly. So that could be useful. And then also local AXI DMA to DRAM and HBM, as this could connect to the NOC on Versal, for example, to access the local memory. And then this will definitely have the application section for adding additional logic. Um, that's kind of at a high level. It's going to take some time to actually implement all this, but that's that's kind of the high level functionality that I'm looking for with these components. All right, so moving on to the new network stack. I don't have a whole lot to say about this because it's still pretty preliminary at this point, but the old UDP-IP stack has some significant limitations. Doesn't really scale beyond 10 gig, 25 gig, because it's not very well parameterized. It takes up a lot of logic resources because the headers are transferred separately from the data. Um, Keeping the headers and the data in sync is, problematic at best due to how it was built. So, I learned a lot since I built that stack initially. So the idea is to take some of that and apply it to building a new stack that's going to be more flexible and more performant. So what I'm thinking is to support IP and UDP natively, but then have a mechanism for supporting, more complex protocols like TCP and RDMA and whatnot. Um, so it remains to be seen exactly how that's going to work. But IP and UDP are just onesie twosie packets. Just one of the That's pretty straightforward. When you get into something like TCP, then you have to deal with streams. So it almost makes sense to have like a separate core um, that can act as a client to the main core for handling that sort of thing. Um, the idea is to have more of a socket style interface, so you can have it'll track the connection state, and you can open connections and such, and it'll handle all the necessary filtering internally, and then to have some sort of configuration via register interface, such that you can integrate this with other network stacks. So the short-term goal is that this will be embedded. The long-term goal is that, well, maybe this can be used inside of Corundum to handle offloading of various protocols and such. We'll see about that. It'll probably have to go through a couple of iterations of revisions and re-architecting in order to get it to a point where everything's going to work. ARP and whatnot, I'm thinking about having that handled by like a soft core or a more compact state machine instead of the relatively large state machine that's used by the current stack. But I guess if you're looking at running this on something like Corundum in parallel with the host stack, maybe ARP just gets passed through the host stack. We'll have to see about that. And seems like embedded RDMA is probably going to be on the roadmap. Can't give too many more details on that at this point, but stay tuned. All right, so moving on to Versal. PowerPoint really wasn't working with me today here, was it? All right. So let's see. The Versal devices, this is something I've been taking a look at for, if we're going to run Corundum on Versal, how would you make it work? Is this actually, gosh, even reorganized my slides. How did that happen? All right, so Versal architecture notes. So the key thing to keep in mind with Versal is that Versal devices like Zincs are not FPGAs. They are ARM SoCs with an embedded FPGA. And this is very important to keep in mind because there are some important differences between the two that crop up here and there. So, like, for example, both Versal and Zinc devices, they boot like an SoC, not like an FPGA. The SoC side then loads the FPGA during the boot process or afterwards. The SoC has dedicated peripherals and I/O pins. On the Zinc, it's got dedicated memory. On the Versal, you've got the DDR memory controllers, which share pins with the PL, but they're hardened. The SoC portion can, in general, do quite a bit of stuff without the FPGA even being initialized. The Versal has some potentially interesting stuff, right? It's got the network on chip. It's got two totally different PCIe subsystems. It's got hardened XDMA and QDMA. Um, but from the standpoint of, Corundum, where we want to be able to mess around with the descriptor interface and whatnot, well, how would we run that on a Versal device? So let's take a look at the PCIe side of Versal to think about how that would work with Corundum. Versal has two different PCIe blocks. One of them is it has the PCIe 4 slash PCIe 5 blocks, and the other one is it has a CPM 4, CPM 5. So some devices apparently don't have a CPM; it's just the PCIe 4. Maybe you can get some with just PCIe 5. I'm not sure about that. So either you have just a PCIe 4, or you have PCIe 4 and CPM 4, or you have PCIe 5 and CPM 5. All right, so what are all these different cores? Well, PCIe 4, it's basically the same as the PCIe 4 cores on the UltraScale Plus. It's located in the PL region. It's got the streaming TLP interfaces. It supports up to Gen 3 by 16 or Gen 4 by 8. Pretty straightforward. Using it should be, I think, not going to say trivial, but straightforward to make even the current version of Corundum run with the PCIe 4 blocks. What does PCIe 5 add? Well, it's exactly the same as PCIe 4, but it adds Gen 5 by 4. Yeah. Doesn't even give you any additional throughput. It's the same aggregate bandwidth, but it supports Gen 5. So, okay. I guess that's kind of cute. What about CPM then? CPM 4, these have both CPM blocks have two PCIe controllers, and they connect to either the network on chip or to the PL. Originally, I thought the CPM didn't connect to the PL at all, but actually you can use it in a TLP bypass mode effectively, similar to the PCIe 4, PCIe 5 cores. So the CPM 4, it supports either Gen 3 by 16 or dual bifurcated Gen 4 by 8, and it has hardened XDMA and QDMA. The CPM 5 is basically the same as the CPM 4, but it adds Gen 4 by 16 and Gen 5 by 8. So it just bumps everything up by factor 2, which actually means it does provide more aggregate throughput, which is kind of cool. The wrinkle with the CPM 5 is that, I guess it's not really a wrinkle, but the notable point of the CPM 5 is that it has dedicated transceivers. The CPM 4 has dedicated transceiver connections, so you can only use specific transceiver sites with the CPM 4. But you could also use those same transceiver sites with PCIe 4 or something else. With CPM 5, those transceivers can only be used with CPM 5, which makes it similar to some of the Intel devices, because Intel has had dedicated SerDes for PCIe in quite a few devices. But Intel supports up to Gen 5 by 16, and Xilinx only supports Gen 5 by 8. So, needless to say, not particularly impressed with these things so far. All right. So, the CPM4, 512 bits TLP interface to the PL per controller. On the highest grade devices, they can do Gen 4 by 16 with XDMA and QDMA. And by highest grade, I actually need to double check the Versal devices. They have speed grade and voltage grade. The tables are quite complicated. I can't remember exactly which devices, but needless to say, it's not the one that comes on the VSK 5000. So it's not really relevant, I think. And it only works with the hardened XDMA, QDMA logic. So yeah, I think the only thing that makes sense for CPM4 is either Gen 3 by 16 or dual bifurcated Gen 4 by 8. CPM5 doubles the TLP interface to 1024, so that's actually similar to the Intel R-Tile, except with half the clock frequency and half the overall bandwidth. Although I guess with the Intel R-Tile, are you going to be able to close the design at 500 megahertz or close timing it with in your design with the clock at 500 megahertz? I don't know. We'll have to see about that. But at least it has the potential capability, whereas the Versal does not. Now, both CPM4 and CPM5 support hardened QDMA and AXI bridge modes. But for the QDMA mode, it doesn't seem like QDMA can be used as a data mover. It seems like maybe you could do that with XDMA, but CPM5 doesn't support XDMA, so that's not relevant. So I'm going to ignore that particular mode. And while they do support AXI bridge modes, there's several problems with that. The first one is that it seems like it's not actually very high performance. If you want high performance data transfer, you're supposed to use the hardened DMA engine. But the bigger problem is that there is no way to access the host memory directly using, or the host address space directly using the NOC because of how the address routing and stuff works on the NOC. There's a few windows that are provided, but those don't even view the PCI address space directly. You have to define AXI bars, which is a range of AXI address space that gets mapped to a range of PCIe address space. You can't just randomly access the entire host memory. So this ends up being basically completely useless because, with the NIC, the idea is that the host is just going to say, hey, this packet is at this address. I want you to read it. And if it's not mapped, then you're screwed. And if you're using the AXI bar, you got to figure out the mappings anyway. So yeah. And as far as I can tell, there's no real way to map to PFs and VFs. So if you want to do something like SRIOV, yeah, I guess you'd have to slice and dice those windows even more finely and have an even smaller view onto the host address space. It's not great. It's not great. I don't know what they were thinking when they designed this thing, but it's kind of terrible. So yeah, the conclusion I think is the only realistic option is like bifurcated CPM4, CPM5, or non-bifurcated depending, in TLP mode, and then we just ignore all the hard DMA logic and the knock and everything else. I guess the knock could be useful for accessing the local DDR memory controllers, but it's useless for accessing the host PCI Express. Um, so at least that narrows down the design space a little bit for Versal. Um, all right, but getting a little bit more concrete, like I've said before, Versal is not going to be supported unless I have a some kind of Versal part. Well, I recently managed to acquire several VCK 5000 cards, and this opens up that possibility. So for those not familiar, the VCK 5000, it's a PCI form factor card with the Versal VC 1902 part. They were initially introduced at a relatively low price for AI inference applications. I think it was like under 3K. It was actually kind of a decent price, as far as some of these large FPGAs are concerned. Especially if you go look at the price of the VC 1902, that's like, dang, that's a good deal. But they made two SKUs available, right? One of them was AI engine only, and a much more expensive one was provided for use with Vivado. So that raises the question: what's the difference between these two SKUs, right? I know Versal and the other Xilinx parts support secure boot features like AES and RSA, such that you can lock the thing down and only run your approved bit streams, or you can keep your bit stream encrypted or something. So my initial thought is, they must be loading their RSA certificate into these things, and using one of these features to lock the cards to only the manufacturer's supplied bit streams. But the cards that I received are marked encryption disabled. So that means most, or if not all, of the security features are disabled on these things. I don't know if it's the same feature with the production boards, because the boards that I received are engineering silicon boards. So I'm not 100% sure about that. But theoretically, if they aren't locked, then they should simply be usable with Vivado. The problem, though, is that there's no public board files or other documentation, at least that I've been able to find. So to use it with Vivado, you got to figure out all the settings, right? So you need to determine the pinout settings, etc. Is this just locked via security through obscurity and or NDAs? I don't know. I don't know if anybody here is familiar with how Xilinx handles those things, but um, yeah.
So,
So okay,
sorry. So just yesterday or day before yesterday, I was
yeah.
trying to download shell files for VCK 5000,
Hmm.
and it seems like there was a form, even though I have access to it, but there's an additional form which you have to first fill up, and then you get access to the website. At least that is what I was able to
Right,
see,
yeah.
but I
So
did not
they,
fill
they
it up.
right, they have lounges for a bunch of things. You got to like request access, and they got to
Mm,
approve you. So
mm,
I think they did something. So I know they did something similar for the VSK 5000. So you can get those files, but you can't just go download them. You got to like
mm,
request access and whatnot. They may need to go check to say, oh, hey, yeah, you actually purchased that SKU, so we'll give you the files or whatever. So yeah, from looking at the fact that the security features, at least on the ES board, are disabled, that got me thinking, well, maybe there's actually no difference between the SKUs. And I had some anecdotal evidence that actually there is no difference between the SKUs.
mm,
It's just how much you pay and whether they give you access to the good stuff. And then also,
mm,
it seems like the board files that are available for the VCK 5000 for the locked SKU are actually software locked in the board file. So like
mm,
if you open it up in Vivado, Vivato's like, sorry, this thing is locked, but
mm,
it's just like a directive in the file saying that it's locked. So like if you were to change it
mm,
or something, then Vivado would potentially work with it. Um,
mm,
and it's like there's really very little in terms of the enforcement over the AI engine only thing. Um,
mm,
but yeah, anyway, I got a couple more slides here. So um, right. So like I said before, with the Versal devices, it's an ARM SoC. So there's a bunch of stuff that's fixed. Right. It boots via OSPI, the octal SPI on fixed pins. The hard DDR memory controllers use fixed pins, etc. So there's actually not necessarily all that much that needs to be reverse engineered in order to actually make use of these things. Um, and the board itself looks kind of like an Alveo, right? There's an MSP430 microcontroller on there. There's a 30-pin debug header. Even kind of the styling of the board is similar to one of the Alveos if you take the top off of them. Um, so yeah, the first attempt, I was able to successfully generate a bit stream for the part and tried to load it on there, but I got a PLM stall. So that's problematic. Apparently, there is some debug info from the PMC that's available during boot if you can get a serial port out. Um, So I took a look at that, and after excluding the pins needed for OSPI, there's only, I think, four potential settings for UART 0 that made any sense to try. So I tried all four, and one of them worked. And the debug info indicated the PL was not starting up. Like, okay, well, that's interesting. There's an image on here that works, but my image doesn't work. So something about the image has got to be wrong, right? It's not like a board level problem. There's got to be something about the image. Um, so I enabled the sysmon channels and I found that the VCC RAM was reading as 0. So one of the regulators was not turned on. But that's interesting because obviously it has to be on for the default image. I don't know why it's not working for my image. The only thing I can think of is that maybe the MSP430 microcontroller is waiting for something and then turning on the regulator as a result of that. But what is it waiting for? Um, well, the card is running a good image, so maybe the settings can be extracted from the good image. I'm not sure necessarily how, but there might be a way to do that, right? I mean, maybe you can read it and then unpack it or something. But Versal's an ARM SoC. Vivado cannot read. Vivado cannot read the OSPI flash. Obviously, it can boot from it, but Vivado doesn't have an option. If you go into the hardware manager, you can write it. You can write it, but you can't read it. So that's a problem. But then I realized, well, it's an ARM SoC. You can just connect to the ARM cores from Vitis and then read whatever we want, including the GPIO pinmux settings. So yeah, we found some other peripherals, and I found an MIO pin driving high. So I added that MIO pin, and then it booted. And then I also managed to get the DDR memory controllers working, which um, was simpler than expected. So yeah, at this point, yeah, I have the DDR working. I have the MIO working. Oh, I guess I also tested the PCI Express interface as well with the CPM, and that enumerates. So the only thing I haven't tested is the Ethernet interfaces, and I haven't tried porting anything over to the board yet. So, um, yeah, at this point, it looks like there is now a path there if we wanted to run Corundum or something else on there that, given enough time, it should be possible. Um, yeah, so I don't know if anybody else has played around with these things or is interested in them, but yeah, um, it seems like if you have well, yeah, so the one downside about the VCK 5000s is that they are an actual, production part. They're not like an Alveo board, which has an alternative ID code that you can target without the Vivado Enterprise license. With these, because they are an actual VC 1902, you need the Vivado Enterprise license to target them. So even if a board just pops up randomly on eBay, if it doesn't come with a license card and you don't have you would need a Vivado Enterprise license. So if you have one or you have access to one, or you can procure one, then they're potentially an interesting board to play around with. Um, I have seen a few of them pop up, not too many, but a few of them. And that was one thing that I asked at least one of the sellers on eBay. Is like, hey, do you know if this is a locked board or not? Well, now we know, or at least we have a pretty good idea that seems like they're not locked at the board level. So now that we have an idea about how to configure them from Vivado, that it should be possible to go that route. And I put all the nitty gritty details over on Zulip. So if you're interested in the process in more detail, you can go scroll through that and take a look. Um, so yeah, at this point, I'll open it up. If anybody has any questions or comments, fire away. Guess I can stop that. Okay.
Uh, so, what's a dual head? Like
Um,
PCI Exi dual head.
right. So the idea, so this is something that I thought of a while ago because it's like if you have, let's see, let me think about the best way to describe this. A lot of the smart NIC designs out there, for example, you might want to be able to kick packets over to, um, well, let me think about this here. There's a couple different ways of envisioning it, right? One of them is that you might want to kick packets over to you know, the hard logic ARM cores for some reason. Another one is that maybe you want the ARM cores to have their own sort of network interface through the main network interface. Um,
Mhm,
so if you have like a 250 SoC where it's a PCIe form factor card, but it has a zinc part on there, with the
mhm,
normal Corundum design, the zinc is not connected to the data path at all. In fact, I think with the normal Corundum design, it doesn't even instantiate those cores, but they are there. So if you wanted to use them, the question is, well, how would you connect that to the data path? How would you make it work?
mhm,
And
mhm,
one of the options that seems pretty straightforward is, well, Corundum has an ARM mode and it has an AXI mode and it has a PCIe mode. Well, if you could use both of them at the same
mhm,
time, then you could have both the host talking to the card and or talking to the NIC effectively, and the ARM core is doing the same thing.
mhm,
And basically, what you could do is from the standpoint of the data path, you could treat that AXI interface as a PCIe VF. I put that in quotes because it's not
mhm,
PCIe,
mhm.
it's not a VF, but you make it look like one, right? So when you're talking
Okay.
about how you route stuff to the different VFs, right, it would just be this VF corresponds to the ARM. Maybe you could even have a couple or something like that. I don't know.
Mhm,
Um, but it would give you the capability of doing some interesting stuff like that. Um,
right,
so you could have logic that's filtering the packets in some way and then sending them either to the host. Well, I mean, it's like if you're going
right,
to do SRIOV, one of the things that you need is some way to filter the incoming packets. Okay,
right.
well, if you're filtering the incoming packets based on the VF, well, you could also send stuff over to the ARM core, right?
Mhm,
And if
mhm.
that just looks like another VF, it just makes everything, very simple. So that's one of the things that I've been looking at is like, okay, so to do VFs, how would you implement that in the design properly, right? And I think the way to do that is to add like an address space ID field to everything. Um, and then that would indicate, you know, where what PF or VF that's associated with, or which interface it's associated with, or which like host it's associated with. So you would map for PCIe, you'd map the address space ID to the PF number and the VF number. But you could also say, oh, this address space ID is AXI, so we'll send this to the AXI interface to the ARM cores.
So once you receive a raw Ethernet packet, who do you send it to, and how do you match that? So the AXI ARM core might have an interface, and let's say
Well, right, yeah. So that's one thing that would need to be figured out. That would need to be figured out for SRIOV anyway, right? It doesn't
yes,
matter if you're using the zinc cores or not, but you'd have to have some sort of a configurable engine that can look at various fields and determine what to do with the packet, right? At minimum, you'd
hmm,
be looking at you'd extract the destination addresses from the packet.
hmm,
You'd either look at, oh, here's this MAC address corresponds to
hmm,
um, the to the zinc, so we'll send it over there. Versus this other MAC address is the host, so we'll send it over there. Um, I don't know. Yeah, it's like I don't know how configurable existing NICs are. If you take an existing say Mellanox NIC that supports SRIOV, how does that handle the filtering, right? Because if you don't do SRIOV, then the NIC doesn't really care about the packet data, right? It just kind of forwards it
mm,
along. You
mm,
don't need to do anything special.
mm,
It doesn't care about the specific receive queue, right? It
mm,
just you can just round
mm,
robin across all the receive. Well, not round robin, but you'd be hashing across all the receive queues. Yeah, round robining is a bad idea because it screws up ordering. Yeah, you want to make sure that each flow only ends up on one queue, such that those packets maintain the same relative ordering. Um, but yeah, so with the filtering, you would want to be able to ideally have like some sort of a hierarchical setup. So you can say, well, um, this particular destination gets sent to PF0, and PF0 has
mm,
eight queues, so you then hash across those eight queues, for example. Um, so yeah, there's a good number of stuff or a good number of things that need to be figured out there. But yeah, so the way I kind of envision it working from a at an architectural level is that all of the RX queues are just there, and you can um, the filtering would send stuff to specific queues or specific groups of queues, and then each queue would be associated with one of the
mm,
with one of the address spaces, right? Be it a PF
mm,
or
mm,
VF or whatever.
mm. Uh, you were mentioning en route to porting the PCI
Yeah.
component to the new taxi library. Mentioned some changes. I wonder what are those changes like? You feel?
Oh, well, so the first thing that I'm doing is I'm converting the strobe signals to like an empty signal because that's going to save some wires. Um,
Mm,
but yeah, the next change that I'm thinking about making is basically changing it. So my original thought about Versal support is that they have this great knock, and if we can just access the host through the knock, then hey, we just need to speak AXI to the knock, and then that'll go straight out to the
mm,
host.
mm,
Well,
mm,
it turns
mm,
out that's not going to work. So that kind of torpedoes that motivation. But I was starting to think about, okay, well, instead of doing this totally ad hoc segmented thing that I cooked up, maybe there's a different mechanism that would make it a little bit more sense. At least in terms of DMA rights, there might be a better mechanism because right now, if you want to write something to the host, you got to write it out into an internal buffer and then tell the DMA engine, hey, read this thing from this buffer and write it out into the host um, address space. And I mean, it
mm,
works, but I don't know. It's not great from a latency perspective, and it seems like it's adding additional complexity. Um, I mean, maybe the alternative is not going to be any better, but I was thinking something like AXI is kind of the right way to do it because I mean, what is AXI? You give it the destination address, you give it the data. That's
mm,
basically what you need, right? You give it the destination address, you give it the data, done. It'll then write the data to that location, and in the redirection, AXI also kind of makes sense, right? Because you give it the source address, and then at some point it gives you the data, right? So
mm,
um, but there are some ordering differences between PCIe and AXI, so I'm not sold on converting it to AXI at this point. So that was kind of my original plan, but now I'm like, actually maybe that doesn't work. But it also got me thinking, well, maybe what I should do is just port the existing DMA engine as close to as is as possible. Um, we'll start building with that, and then you know once we have a better idea of what the requirements are, um, then we can swap out because I it's
mm,
Corundum initially was built with AXI internally, and then I swapped that out for this segmented thing. So there is precedent for doing that. I've done it before to swap out the internal um, DMA interface infrastructure. So we'll see.
mm.
Done it before. If I have to do it again, I'll do it again. But yeah, I think the important thing is we got to figure out exactly what that needs to look like and what the performance requirements are.
Okay. Because I was thinking that are you going to redesign things on the TLP level? Because I remember because I have watched the PCI video from you, the lecture of your lecture on PCIe couple of times. So I wanted to know if there's a redesign in the whole TLP handling session.
Oh yeah, all right. So the TLP handling stuff. Oh yeah, so that's another thing I was thinking about. I think I'm going to port that over as is for now, but then I think most of that is going to be rewritten. Um, and it's mainly going to be
Hmm.
rewritten for like performance reasons, right?
Hmm.
That's another thing I've been trying to figure out as well is with the DMA engine right now, the actual DMA engine itself doesn't do any segmentation on the TLP end, um,
Hmm.
which makes sense because it makes the DMA engine simpler, but at the same time as you start getting up into these much wider interfaces, that could end up being a problem, right? If you're talking
Hmm.
about like the Agilex I series or even the CPM5 with a 1024-bit interface, you might need to start putting multiple, TLPs per cycle, even for DMA operations. So
Hmm.
yeah, and the way I have some of those modules written, they're pretty terrible from a timing perspective. It took a lot of work to get them to where they are now, and I think it kind of crappy the way some of those are put together. But from the work with Carlos and trying to build this packet switch, I think we've learned a few more techniques for handling packets and dealing with stuff out of order and whatnot, in terms of the buffer management and whatnot. So I think some of those approaches could be applied to, I think, you know, a lot of the interconnect type stuff, right? The TLP
You
FIFOs,
mean?
where you're dealing with the segmented stuff, the TLP MUX and DMUX modules, and I think also maybe
Hmm.
the AXI and AXI Stream crossbar modules and such could also benefit greatly from some of those techniques.
Hmm.
So
Uh, uh,
there's a lot of stuff that just internally I think there could be a lot of improvements that are made, but I think a lot of those improvements can be made without significantly changing the external interfaces.
hmm. Uh, so I have just two more questions from your previous video. As far as I can, so the previous video about QNIC, in which you
Right,
introduce
right, right.
what's
Yeah,
QNIC, I think that's a, uh, uh, I did not understand whole lot, but I do have a question. So, the DAC and the ADC chips that you have on the board that
yeah,
you plugged into the NIC,
yeah.
the sample speed, is there a calculation behind that sample speed? Did you guys pre-calculate it? Because
The
you knew,
the
okay,
the
this
the
is a
sam
transmission.
the sample rate of
Yeah,
1 gigasample per second.
yeah, yeah.
That's
Did you
just what the
pre-calculate or okay,
that's just the rate that they run at. I mean, yeah, I guess
right?
you can mess around with the PL configuration and run at a different sample rate, but the ADC is a 1 gigasample per second ADC is the DAC. I think the DAC will do like 2 point something, but for a variety of reasons, we just ran it at 1 gigasample per second. Like, it doesn't really make a lot of sense to make them different. Um,
Hmm.
for RF, you can do. So the thing is, with both of these chips, they have a bunch of additional internal logic that can be used for mainly for RF applications. So if you're trying to do like
Hmm.
for RF, you'll do like block up and down conversion and things like that, and some basic what do they call it? I'm drawing a blank on what the term is, but you can rescale the INQ components and IQ
Hmm.
impairments. No, I guess the opposite of that. I don't know. Um, there's some basic blocks in there that can do some DSP to make some adjustments, but it's all for RF applications. So for RF, you can do block up and down conversion with these things, and if you're doing a block
Hmm.
up conversion with the DACs, okay, well now you're not actually giving the DAC the actual samples it's outputting. You're giving it maybe not baseband samples, but lower frequency samples that then get up converted. So you can actually
Hmm.
run the JES interface at a much lower rate than the full,
Hmm.
1 gigasample per second times 16 bits times four converters. Um,
Right.
so if you put it in that kind of mode, then yeah, you can run it at 2 gig samples per second, or I can't remember what it tops at. It might be 2.2. Um, but yeah, with the JES interfaces, the the link rate is related to the sample rate. They're not necessarily
Hmm.
completely decoupled. So if you, I mean, I guess you could run slower than what the link rate supports, but it's like if you wanted to run the ADCs at 1 gigasample per second and the DACs at, I guess you could run it like 1.25 or something like that, or 1.5. I can't remember. There was, they have different limitations on the link rate there. So if you wanted to run the DAC at the maximum link rate, it ends up just being a pain in the butt in terms of how stuff needs to be configured on the JESD cores. So with things
Hmm.
are the way things are currently set up, it's nice and simple. The internal clock is 250 megahertz. There's no clock domain crossings, which is pretty cool because all
Hmm.
that happens inside of the JESD cores. So all
Hmm.
that entire data processing thing is all one clock domain. All the DSP stuff is one clock domain. Um, and then yeah, we just run at 1 gigasample per second. Now the actual
Hmm.
data rate that we're running at over the link is only a few megabits per second, right? It's because we
Hmm.
have quite a few
Right. That's
samples
enough.
per
Right.
symbol.
Hmm.
Because yeah, the whole point of this thing is not necessarily to build a communication link; it's to be able to do these quantum measurements. And
Hmm.
so I keep having to to bang that over the heads of some of the people on the team. It's like, look, we're not trying to build a communication system here. Yes, there are techniques you could use in the communication system to, really try to recover the data bits, but we're not trying to recover the data bits. We're trying to make these other measurements and transmit
Hmm.
data at the same time. So it's kind of a different set of restrictions there. So yeah, and I guess we're in the process of purchasing another FPGA board. In fact, one of the high-tech global FPGA boards is one of the Zinc RFSoCs, which has data converters that I think are 14-bit but 5 gigasample per second. So, and the funny
Hmm.
thing is, those boards are actually cheaper than the previous board we were using. But they also have more channels. I think they have 8 ADC channels and 8 DAC channels, so that's going to be good. And we don't need to deal with JES because there were some issues with the JES setup. Wasn't as reliable as I was hoping for. But yeah, with the Zinc, we shouldn't have that problem. So, um,
Uh,
One
uh,
second, sorry.
yeah,
Just to
yeah.
say goodbye because I have to go. But very
yeah.
Oh,
interesting meeting. Sorry.
all right. Well, sounds good. See you later, Carlos.
See you. Thanks.
See you.
Good luck with your PhD stuff.
Thank you very
Hopefully,
much.
get
I'll
that
keep you up to
polished
date.
off without any major problems. Yeah. All right.
Sure. Thank you.
So, whenever you mention about supporting TCP, I think so. Whenever you say supporting TCP, I kind of have in mind that I know you mentioned before, it's not the whole TCP stack. It's just as usual, Nick, some primitives of
Right. So okay.
TCP.
Well, so if you're talking about the stack, well, this would be an embedded stack, so it would have to be the whole protocol for the embedded
Right.
stack. But the idea with the stack is not necessarily to support TCP, but it's to support is to have an architecture that would be able to support TCP.
Hmm.
So we'll have some sort of an interface where you can connect another module, which can then implement the TCP stack.
Hmm.
When we implement that module, if we ever implement that module, I don't know, right?
Hmm.
But it's
Hmm.
like there's some interest in RDMA.
Hmm.
So the plan at least is to build something that does not just UDP/IP, but we can also add RDMA support to it. So I've been thinking, well, what other protocols might be interesting? Well, people build TSO units,
Yeah.
right?
s-
TCP offloading, or not TSO, TOE, right? TOE, right? So something like that,
Hmm.
could potentially slot into this. RDMA could potentially slot into this. Maybe there's other protocols as well that could be interesting. But
Right.
yeah, the
So,
idea is
so
from the get go, we're not going to implement TCP, but it's like, okay, we're going
yeah.
to try to design this as if we were going to implement TCP in the future, just to make sure that we have that as an option.
Right. So, I've been looking into this something called reliable UDP. I don't know how reliable it is, but it seems like it's a cut down version of TCP. And it seems so. I'm thinking to play around with it because I know. So I've been also playing around with TCP stack, and it seems very complicated, at least. So I think jump from a UDP to a reliable UDP will be much
I
smoother
mean,
than
I
this.
I think really anything above and beyond UDP is going to get very complicated very quickly, right? Because UDP is literally
Right.
just sending and receiving packets. I mean, what is there
Right.
on? That's like the most fundamental thing that you can do, right? Like, what is UDP aside from just adding some ports onto just sending and receiving packets, right?
Right.
Um,
Right.
and so what did you say that protocol was called? Reliable
Reliable
UDP.
UDP. Yeah.
So
Yeah.
what does UDP stand for?
It's a
That's kind
yeah.
of it's kind of
Yeah.
hilarious. If you expand it, it becomes reliable, unreliable
Yeah.
datagram protocol.
Yeah. Data diagram. Yeah. 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 True. Yeah. But
But
yeah,
I mean,
true.
well, so Google, they have their Quick protocol, and that sits on top of UDP, right? So
Hmm.
um, yeah, by saying, TCP, it's like, well, you could put any other more complicated protocol in there, right? You want
Hmm.
UDP, you can do that. You want TCP, you can do that. You want Quick, you can do that. Um, so yeah, it's figuring out, what do these protocols need from the standpoint of the network stack, and making sure that you have interfaces and infrastructure to make it work.
Hmm.
Um, yeah, and so like for example, one of the things that I'm thinking about with this new stack is, instead of having separate header and data interfaces, you have the
Hmm.
header in line with the data, and then you can also potentially have the stack strip it off. So if in the UDP mode, you would only see the UDP header and then the data. You wouldn't see any of the
Hmm.
Ethernet headers from the application that's connected to it.
Hmm.
Because that's kind of a weird thing with the current stack, is that all the ports are there, but you know, from the client application that's receiving a UDP packet, generally you don't need any of that besides maybe the UDP ports and the addresses. And then when you're sending it, well, everything else gets filled in by the stack. So you get kind of this weird thing going on. And then it takes up a lot of additional logic resources for all these wires, especially as you shrink the data width down, right? If you think about 8 bits wide data
Hmm.
plus this huge interface for
Hmm.
the header, that's not very efficient. So yeah, that's kind of what I'm thinking about with the new stack. And then the idea is that you could also use like the TID, TDESP signals and whatnot to associate with
Hmm.
connections. So instead of the user application logic having to keep track of which addresses, which connection or whatever, you just have the TID. If you get a new value, then that's a new connection or whatever.
Hmm.
There might be another interface saying, "Hey, we got a new connection," or "Hey, this connection closed," or whatever. So there's still some things that need to be figured out, but that's kind of the goal, is to make it. The previous one is
Hmm.
just kind of a collection of pieces, a collection of parts, and you put them together and you can make some stuff. But with the new stack, the idea is to have something that's a bit more of a core you can just drop down and connect stuff to.
Hmm. Hmm. Okay.
And then I guess one thing I didn't mention on that slide, but the idea is to do it in such a way where we might be able to integrate it alongside Corundum,
Hmm.
for offloading purposes and whatnot, and have it interface with the host stack in some way.
Hmm.
But yeah, I guess the other thing I should mention is that we're probably only going to start out with 10 gig and 25 gig support. And maybe similar to
Hmm.
Corundum, we may have different variations of it for different data rates, where you can trade off
Hmm.
the resource consumption appropriately. Because at low rates,
Hmm.
right, at 1 gig, you got 64 clock cycles per packet minimum, right? So
Hmm. Hmm.
that is ages on an FPGA.
Right.
But at 100 gigabit per second, you could be getting one packet per clock cycle. So you got to be,
Hmm.
you got to do a lot of
Hmm.
work to keep up with that. And at 400 gig, yeah, you could get multiple packets per cycle potentially. So yeah, um, I guess that is a design consideration as well. Is does it make sense to support these really high throughputs of the really small packet sizes? I'm not sure.
Hmm.
Um, but yeah, that's that's probably one of the biggest differences between like the different versions of Corundum, is not the data rate so much as like the packet rate that it supports, and probably a similar
Hmm.
thing with the stack. But
Right.
it's still kind of preliminary. We'll see how things pan out.
Hmm. Yeah, by the way, I was recalling what was the difference. One of the major difference was the TCP options, which itself is very weird, right? Because TCP, how you calculate TCP options, you have no guarantees how long it's going to be, right? So the calculation of the whole packet, it becomes
TCP option,
very,
yeah, yeah. All of the optional headers are just a gigantic pain in the ass from a hardware
yeah.
perspective. Like none of these protocols are designed with hardware in mind. They're all like, oh,
Hmm.
it's software running on a CPU, so we can just have some offset pointer in here. We can walk this big long
Hmm.
list, yada yada yada. Who
Hmm.
cares? But then you sit down and
Hmm.
try to implement in hardware. You're like, yeah, I wish there was a way to
Hmm.
slap somebody through the internet. Like, who the hell thought this was a good idea? uh,
So, thanks, thanks.
it's like,
It's
here, help me write this damn thing because you designed it in the first place. ah, you designed it. Now help me parse it efficiently. Yeah, I think Quick is particularly bad with regards to that because they use some weird encoded, TLV thing. I can't remember what it is off the top of my head. Somebody was asking me about it a while ago, like, hey, can we decode this thing? I said, it might not be, was it quick or was it like a new one of the recent revisions of the HTML? It might have actually been the like HTML 5 or 6 or whatever, or no, not HTML,
Mm-hmm.
HTTP, which runs on top of Quick, and they have some very complicated mechanism for transferring information. And
Mm-hmm.
it's like, okay, I guess it's not too bad from a software perspective, but from a hardware perspective, it's like, ugh, because all the fields are variable length. Everything is variable
Mm-hmm.
length, and in hardware, variable length's X.
Yeah.
I mean, the whole packet can vary in length. Okay, that's fine. But if stuff's moving around and all these little fields are different
Mm-hmm.
lengths, like, not good, not good.
Good.
Yeah, especially if you want to
Great.
have reasonably short pipelines. What are you gonna do?
I just want to say, Alex, great work. It's
All right.
it's a lot of
Thanks.
work.
I'm just glad I had some new stuff to talk about today. Because some of these other meetings I keep seem to be recycling a lot of the same stuff because it's like there's so much other stuff going on. But yeah, this time things are I, things have been taking place, and I had some good stuff to talk about. So that's good. And thanks to everybody for tuning in. Anyway, I guess I'll go ahead and clear out of here then. If there's no more questions or comments or anything else,
I
if anybody
just,
wants to say anything.
sorry.
Oh, hey.
I just, well, I just was interested if you had any chance to look at the transceivers on Versal for Ethernet.
The
Uh,
transceiver's on Versal for Ethernet. It's on my to-do
not,
list. My understanding is they're quite similar to the ultra scale ones. Although I guess it probably depends a lot on which Versal part because they have a couple different transceiver types depending on the part. The only boards that I have right now are the VCK 5000 ones, which I think have the GTY or GTYP, something like that, which I think is very similar to
yeah,
the
I only heard the two of them, GTY and GTYP.
yeah, but Versal also has the GTM, which is the PAM4 variant. Let me just pull up the datasheet on that really quick. Um, go to Xilinx, Versal. All right, so and then they have their weird naming for these things, AM whatever. Yeah, so they have the GTM ones. I guess I need to check what parts even have those. Uh, oh, it's not so easy to look up, is it? Um, so AI core. Yeah, AI Core is only GTY and GTYP, so I think it's the Versal Premium that has the GTM. Um, but yeah, so all the ones that I have are only the GTY devices, the GTY transceivers. And my understanding is that GTY transceivers are quite similar to the ones on the UltraScale Plus devices. So it should, I think the interface, the way you talk to them is a little bit different. Um, they maybe more the way you generate the cores is a little bit different. Um, but I think the actual data path interface should be more or less the same. Oh, there it is. It's AM002. I don't like the way they've released these architecture manuals. It's like the GTM is AM017, the GTY is AM002, so it's in a completely different spot in my folder here. Um, yeah, so these things, I guess they have some differences in the PLLs. They have an RPLL and an LCPLL per pair, instead of a shared pair of QPLLs for all four channels, and they don't have CPLLs, which is probably good because the CPLLs are kind of terrible. Um, but I think in terms of the actual serializer, they are quite similar. Well, I'm looking at this. All right, so what do we got here? TX interface buffer. They got so they have actually more support for 6466 in the hard logic. but I'm thinking it probably makes sense just to roll um, with the same wrapper code that I have now, or keep it as close as possible, and just use the synchronous gearbox and asynchronous gearbox directly instead of trying to use more hard logic in the transceiver. But yeah, I think other than that, they are pretty similar in the capabilities. I don't know. It'll probably become more clear once
Maybe.
I actually try to use them.
Yeah,
So
would be interesting to know.
yeah, no, I mean, I think the really interesting ones are, it's like if I get a V80, I think that one has the PAM4 series of GTMs on there. So that's definitely going to be
Ah,
interesting. Um, but with the VCK 5000s, yeah, with the GTYs, I mean, I'm from looking at the documentation, I'm not seeing any major roadblocks. But you never know until you actually try to build the darn thing. Anyway, um, yeah, I'll certainly post on Zulip if anything interesting pops up. So as long as you're on there, um, you'll know about it as soon as I know.
yeah, thank you.
Yeah, sure. Do you have any Versal boards that you're playing around with, or you're just interested in general?
Oh, just interested. I do have this Alinx, or I don't know how it's called, just cheap Chinese board with Versal.
Oh, is that one of the Versal AI Edge parts?
Yeah, yeah.
Ah, okay. Yeah, I was looking into getting one of those boards until I got the these VCK 5000s. It still might be worth getting one. Um, but yeah, those look like they're actually a pretty darn good deal, right? Because I think they have the PCIe 4 core on there plus some Ethernet interfaces presumably. So,
Yeah, they only go up to 10G, I guess, because maybe of
oh,
some limitation because it's a SOM module. I don't know. They only say 10G maximum.
let me see if sometimes it's a package limitation. Um, so like it has the GTY the raw transceivers can potentially go faster, but what part is on there?
Yeah, transceivers are capable of 25G, or just
Ah, I see. But the SOM can only do
the
10.
board itself. I
Well, I mean,
already see some problems with the eye on 14G, so
hmm.
I didn't even try 25G. So
Yeah, that might be. Yeah, I guess if you really want to do like 25G, you need the proper connectors for the SOM to the main board and whatnot. So that could be the main limitation is that sort of thing. Yeah, the board design and the SOM design. Um, so it wouldn't surprise me if they're using the cheapest connectors they could possibly find. So, if that's the case, you're probably lucky to even have it working at 10G, I would think. Well, you said you have problems with the eye, so I guess have you
well, it's
seen?
okay on 10G. It's okay. It starts on 15 and up.
Ah, I see.
It
Oh,
goes
you're trying to
better.
see how fast you can get it to go. Yeah.
Yeah, I tried different frequencies just to see what can I do.
And were you just running that with a loopback and then the iBert or something? Or
Yes, yes.
gotcha. Okay. Yeah, having
Yeah,
that kind
I
of
had some plans to try to port this Corundum stuff, but yeah, didn't have time for that yet.
it's fine. Yeah, it's really nice having the eye scan capability on those things and being able to look at the signal quality right there on the actual device. Without that capability, it sucks. You need very expensive scopes. And even if you have very expensive scope, being able to probe it is a problem. So yeah, being able to extract that
Yeah.
right at the receiver is hugely useful. Um, yeah, so I guess they have VE. Well, so what's the part on there? It's one of the VE 2102,
2302, I think.
2302. Okay. Yeah, so this says it has GTYP transceivers. I don't see any notes about the transceiver data rate. Some, at least on some of the older parts, they would have notes in the product selection guide about transceivers being limited to certain rates. So if you got, they'd have like 3 or 4 different packages available, and depending on which package, the transceivers would be able to run at different rates. So yeah, I guess for these AI edge devices, it's not limited by the package. So yeah, I guess in your case, it's limited by the SOM. That's annoying. And then I guess it has one PCIe core, which, okay, fair enough. It's a relatively small part, so that makes sense. Do you have any hard Macs on there? I don't know.
It has MR
It
one
says there's
instance.
okay, so I guess they have a few different variants of the MR Mac. So this one says there's a 40G multi-rate Ethernet Mac. I mean, I guess, well, with a Gen 4x8, ostensibly you could do 100 gig on that. That would be technically enough bandwidth, but they don't give you any 100 gig max. Well, I guess that's how they got to do their product differentiation. You get a Versal AI Edge, now we're not going to give you 100
Yeah.
gig.
But
What
on
are you gonna do?
such small chip, what would you do with 100 gig?
Well, right, yeah. I understand you got enough PCI Express bandwidth to do pass it through, but yeah, that's true. It's not that big of a part. All right. Well, if anyone else has any questions or comments, fire away. Otherwise, I guess we'll call it a week or call it a day.
Have a good weekend, Alex.
All right.
You deserve some rest.
Sounds good. All right. Well, going once,
Bye.
going twice. I guess that's it. Well, we'll talk to you guys later. Thanks for tuning in. We'll keep in touch on Zulip. See ya.